Hello friends, welcome back to our channel Abhi Chemistry Tutorial. So today in this video I am going to discuss about atomic force microscope. So if you are new to our channel, please take a second to subscribe to our channel and start watching the video. So coming to today's topic, it is atomic force microscope. Simply we can represent it as AFM. Looking about the history of atomic force microscope, in 1981 G. Binning and H. Rotter invented the scanning tunneling microscope, which was awarded Nobel Prize in 1986. So STM. It was the first microscope invented by G. Binning and H. Rotter, and the modified version of the STM microscope is called atomic force microscopy, which was invented in 1989. So even in some AFM machines you can see the STM mode and AFM mode. So STM and AFM are almost working on the same principle, but atomic force microscopy is the modified or upgraded version of the STM. So the main use of AFM is to characterize the surface morphology or the surface structure, and most importantly the roughness of the surface can be studied using AFM, and the general morphology which is used to measure the film thickness. So mainly they are used for films. So coming to sample preparation, the size of the sample should be 8 mm by width and 8 mm by length and a height of 1 millimeter. So in this size the sample must be prepared. So the sample should not be simply a solid, but it should be drop casted. That is, it should be made into solution or dispersion, and it should be drop casted on a small mica sheet, and then it can be pasted on the sample holder using a carbon double side tape, and then you can introduce into the sample chamber in the AFM. So coming to the principle and working of the atomic force microscope, here you can see the sample table. The sample is the green color. It's represented in the green color, and you can see a small needle-like structure called cantilever. That is the cantilever, and the sharp tip you can see, it is said to be cantilever tip. So this cantilever tip is the main portion. So this cantilever tip is the main part which is involved in the atomic force microscope. So the atomic force microscope consists of this cantilever with the sharp tip, and it is used to scan the specimen surface. So the cantilever is made up of silicon or silicon nitride, and the radius of the tip will be in the order of nanometers, which is not visible through our naked eye, but the AFM is connected to a software in the system. So using that, there will be a camera through which you can clearly see the tip of the cantilever, and also you can check whether the tip is placed directly above the sample, and you can also select the proper place where the cantilever tip has to scan your sample. So there will be also a laser source. So this laser source will be directly falling onto the cantilever, and from the cantilever the light reflects to the photodiode, and from the photodiode it travels to the detector, that is the system, and from there you will get the proper image of the surface of the film we have taken or the sample we have taken. So when the tip is brought near the sample surface, the force between this cantilever tip and the sample will lead to deflection of the cantilever, and this deflection is absorbed by this laser beam, and this is what recorded on the system. So the piezoelectric crystal PEZT, which is represented in the black color structure, is a piezoelectric crystal which actually controls the movement of the sample table up and down. The AFM image can be taken in two phases, mainly the height mode and the phase mode. So the height mode gives the surface topography of the sample taken, and the height mode gives the depth of the sample or the height of the film, that is the thickness of the film. So according to the Hooke's law, force is equal to minus kx. So F is the force acting on the cantilever and k is the cantilever spring constant and x is the vertical displacement of the end of cantilever. So as I said before, a piezoelectric crystal raises or lowers the cantilever to maintain a constant bending of the cantilever. So the piezoelectric crystal is the controlling system for moving the cantilever up and down. Actually, we say the cantilever is moving up and down, but the real case is that in the case of an atomic force microscope, it is the sample table, that is the sample which is moving up and down towards the cantilever tip. But we actually say the cantilever is moving up and down while we are explaining the concept. The force exerted on the tip varies with the difference in the surface height. So in some areas the height will be little bit higher and the other area will be somewhat deep over the film. So depending on that, the force will also change. And as I said, a laser beam is constantly reflected from the top of the cantilever, and this reflected beam is sensitized by a photodetector consisting of 4 side-by-side photodiodes. And here you can see the simple atomic force microscope. So it is the laser beam that is reflecting from the surface of the cantilever which is detecting the bend occurring in the cantilever, and it calculates the position of the cantilever. So while the cantilever moves up and down, up and down, up and down, touching the surface of the specimen we have taken, finally it will produce the reflected laser beam will also show the same sort of deflections, and using this readings the software is going to produce the proper image of the specimen we have taken. So thus the AFM records a three-dimensional image of the surface topography of the sample with the maximum resolution and also without causing any damage to the sample surface. So there are three modes of operation for the AFM. The first one is contact mode, the second one is non-contact mode, and the third one is the tapping mode. So the contact mode, as you can see in the figure, it is touching the surface, and non-contact mode is not at all touching the surface but it is scanning the surface. And tapping mode, it is just going up and down by just keeping a small touch with the sample. So we will explain in detail. So the first one is contact mode. So the contact mode means the cantilever tip is scanning over the surface of the sample by contact. That is, the cantilever tip is touching the surface of the sample and it is moving so that the laser is falling on the cantilever tip and the reflected beams will give us the surface topography. So the tip makes a soft physical touch or physical contact with the sample and the scanner gently traces the tip across the sample. But there is a disadvantage in this method, that is, in case of biological samples like cells, if you are using, then if contact mode is used, the tip can damage the surface of the biological samples. That is, the general integrity of the delicate biological samples can be lost, and also the resolution obtained in contact mode will be very low. And the next mode is tapping mode. So as the word represents, tapping, just touching, and the tip moves up, the tip moves down, gently taps the surface, and again it moves up. So in this way the cantilever tip traces and retraces the specimen 2 times and thus give us the scanning image. So in their case, in all the 3 modes, there are 2 types of scanning, that is tracing and retracing. That is, one is going forward and the other time the same tip is coming backward, thus the particular surface is scanned twice and we are getting the image. Okay, tapping mode. So this provides a high resolution topographic image. So the cantilever lightly touches or taps on the sample during scanning. The tip oscillates vertically contact the surface alternatively and then lifts off. The amplitude of oscillation in case of tapping mode ranges from 20 nanometer to 100 nanometer. So here also the tapping mode is again classified into tapping mode in air and tapping mode in fluids. So tapping mode in air is for some ordinary samples like polymers, and for tapping mode, and the tapping mode in fluids is useful for biological samples like cells, proteins. And the third mode is non-contact mode. So as the name suggests, the cantilever tip will not touch the surface of the sample, but it will scan just above the surface of the sample. So the cantilever oscillates above the sample surface, but it will not touch the sample. So the resolution can be obtained under ultra high vacuum. So in biological studies, this tapping and non-contact modes are used. Since we already learned in the contact mode that in case of biological samples, the general integrity of the sample may be lost by the tip of the cantilever touching the samples, biological samples. So in case of biological samples, only non-contact mode and tapping modes are used. So coming to the applications. So the main application is the morphology. So we can study the morphology. We will get an image of the morphology of the sample we have taken in a submicroscopic level. So we can see if there is a smooth surface or if there are some depths or grooves or pores or whatever it is. All the morphology we can study using AFM. And next is the surface roughness calculation or quantification. So the roughness of the surface can also be found using AFM. And to study the physical properties like swelling, cohesiveness, smoothness, and in case of biological samples, so to study the mechanical properties of cells, tissues, microorganisms, and protein, and to study the morphology and investigate materials like composite glasses, ceramics, polymers, and semiconductors. So these morphology of polymers, glasses, ceramics can also be studied. So it is also used to study abrasion, cleaning, adhesion, etching, lubricating, plating, polishing. AFM can image surface of the material in atomic resolution, and it can also measure force at nanonewton scale. That is a very small range. The biomolecular dynamics can also be studied. The quality control of blend synthesis compounds can be studied to study the unfolding of nucleic acid strands, and also used to study the adhesion properties of soft matter, to study antibody antigen binding and localization of ion channels, and to study the surface frictional forces. This atomic force microscopy can be used. So this is all about the history of the atomic force microscope, sample preparation, and the principle of working, and also the modes, three different modes of working in atomic force microscope, and also the applications of atomic force microscope. I hope you understood the topic. If there is any doubt regarding this atomic force microscope, you can leave your questions in the comment section and I will answer you. So if you like the video, please give a like and share to your friends, and don't forget to subscribe to our channel, and see you all in the next video. Until then, thank you. Bye.